is negative and volume is positive.
Yeah, but so it's saying the sign of pressure work done by the system is positive, and it's a true or false. I chose false. It's supposed to be negative, but that's incorrect. It says.
Okay, I'll take your look into that.
All right, thank you.
This meeting is being recorded.
All right. Good afternoon again. Let's see. Example 6. Going back into it. Example 6 says that calculate delta H universe at 25 degrees Celsius. So that's why we have to take 25 degrees Celsius. Example 7 says calculate delta S universe at 352K. So that's when we'll do it 52K. So that's the difference between the two. And this is going to be spontaneous reaction. And this is, this here is going to be at equilibrium. And this is going to be at lower temperature. So this is, we're talking about formation of methane. Forming methane. So we wrote down the equation here. C graphite plus 2H2. Yeah, I don't want to do that. Let's do it over here. C graph plus 2H2 gas giving us CH4 gas. Now, calculate the universe for formation of methane from its constituent elements 25 degrees Celsius. So that's what we are doing. Formation of methane, we want to find out if this reaction is spontaneous or not. How do we find that out? By knowing if the delta S universe of this increases because of this reaction, then it's spontaneous. If it decreases, then it's not spontaneous. That's what that means. Okay. Molar entropy of C graphite is this, that of that, and that of that. And C, we took care of that, and we calculate delta S of the system. And that worked out to be negative 80.80 joules per Kelvin. So far, so good. Now, this worked out because we did it at 25 degrees Celsius. We are told to do it at 25 degrees Celsius, 298. So that's when it works out to be 0.8. Now, delta S surrounding equals negative delta system divided by T. Now I have a little problem here. The delta S system is 74 and negative would be positive. This would become positive number. So this is what would become delta S sur equals negative delta H system divided by T. So negative delta S system would be negative of the negative, so it will be 74.87 kilojoules divided by 298, not 323, because we are told that 298 K. And that works out to be negative 80. So it's worked out actually positive 80, not negative 80. So there is a mistake there. 80, 80.8, 80.8.
Professor, you did this one already and example 7, I believe. Are you just going back to refresh or?
Going back to 6 because I found when I was thinking about it, there is a mistake here. This should not be negative. This should be positive.
Oh, okay.
And we converted this into kilojoules into joules. That's what we did already. So 80.8 joules per Kelvin.
Isn't that equal to 250 joules?
Sorry, 250 joules. I'm going up there. 251.2 joules. Okay. So now we add up these two, this and this one and that one. So 252 plus negative 80.8 equals 251. $170.4. $170.4 joules per K. Yeah. Okay, what does this mean? This means the reaction is spontaneous. That this reaction would happen, this reaction would happen at 25 degrees Celsius. It's spontaneous. That's what that means. Because this is positive. Now we go to number 7. Calculate same thing, same way of doing that, of the process. This is different. This is methane. This is alcohol. Alcohol converting from liquid to gaseous alcohol at 352 Kelvin. So here we have, this is the equation. And at equilibrium, delta S surrounding equals same thing. So we need to find out delta S system and delta S surrounding. That's what we have to find out. The delta S system is given us to over here. Delta H system is given us here. This is delta S vaporization. That's the system. And it is positive because you have to put energy into it at 352 Kelvin. You have to heat this alcohol. So that's why it's positive. So divided by T, so delta S, let's see. Here we can write it down right here, okay. 38.6 kilojoules. And it's just for 1 mole, so we won't write that mole, we'll just understand that. Divided by 352 Kelvin. And that equals, we're gonna convert that into joules now. 110. 110 joules per Kelvin. Ah. That's delta S surrounding. Delta S universe equals delta S surrounding plus delta S system. Now we know the surrounding is that. (110) joules per Kelvin, and we need to find delta S system. Delta S system is 109.7 right there. So minus now one of this I am confused right now.
Is there supposed to be a negative in front of the delta system divided by temperature?
That's what I thought, but I don't see it. So this is delta S vaporization of this process is 36.8 kilojoules per mole, and this is heat is you will have to heat it. So this is positive number here. This number is positive here, and this number is delta S system is given to us as positive. So I don't know if there is a typo here someplace. That's the only thing I can think of. Let me come back to it on Wednesday. I need to look into it and see what's happening here. Okay. Criteria for spontaneity for exothermic reaction. We were talking about that. And these two criteria, spontaneity, delta S system divided by T and delta S system. These two criteria together create a new state function. That's what we talked about. We're putting it together, we get delta G. So delta G equals negative T delta S universe. That equals delta S system minus T delta S system. And so this is what we talked about. Okay. Example 8. What's example 8? Why example 8 again? Should be example 8. Example 9 here. Oh well, we won't worry about that. Okay, combustion of octane at 25 degrees Celsius. Now we are talking about what's happening in the car. Gasoline is a mixture of chemicals. It is not a pure substance. One of the compound in gasoline is octane. So we can kind of say that, okay, gasoline is all made up of octane. And then we calculate the delta G of the reaction. That's what we are doing. Delta G system for combustion of octane at 25 degrees Celsius. The heat of the reaction is this. That's the heat of the system right there. Temperature is 25 degrees Celsius. Delta S system is this. So we just plug in the numbers. So heat of the reaction is given. So that's heat of the reaction. Heat of the reaction. And then T delta S reaction is given here. This can also be calculated. Both of the heat of the reaction and T delta S reaction can be calculated also. Anyway, it's given here. Temperature is 25 degrees Celsius. So that's 25 degrees Celsius. Now this is joules and this is kilojoules. So the main thing is for us to make sure that this is converted into kilojoules. And then when we do that, the math, that works out to be this much energy is available to move the car now. Okay, let's do this thing here. This is gonna be a negative number over here. That's what the problem is. Dang. This is negative here. This is negative here. So that's a negative, negative plus negative. That's a negative number. And it's also energy available to move the car. This much energy is available to move the car. That's what it means. And this is different than how much energy is produced by the reaction. This is different than delta H of the burning of octane. This is what is available as work to do the work. Now we talk about Gibbs free energy. One more state function. That's the last state function we're going to talk about for now. Why delta G is important? Because first of all, it is a state function. So it's very easy to calculate. What do you mean by very easy to calculate? We say final minus initial. Final minus initial. Final state minus initial state. So what do we mean by final state over here? What do we mean about final state? Meaning delta GF of formation. Like delta H of formation, there is also such thing as delta G of formation. It's forming one of mole of a compound from its constituent elements. How much energy is available to do work? So the final state is going to be the sum of all delta GF of the products of product minus sum of delta GF of reactant. This equation is very similar to the equation that is equation for the heat of reaction. In the heat of reaction, we would have sum of, instead of delta G, we will have delta H. Delta H, heat of formation of product minus sum of formation of reactant. So that's a extremely similar here, just instead of a H, we have a G. And here H, we have a G. That's all there is to it. So both equations are pretty much exactly the same. the third equation for entropy is not the same. So delta S for the reaction, it would be sum of entropy of the product minus sum of reactant of the reactant, sum of S of reactant. And there is no delta here and there is no formation. Entropy does not get into formation. Entropy, everything is entropy because everything's temperature is more than 0 Kelvin. So we have entropy everywhere, and our entropy is positive, and so it's just S. So these are the three equations that are the important equation, and these two of them are very similar, whereas the last one is not. Sum of and sum. Okay. Example 1, calculate delta G of the reaction between carbon and oxygen. Carbon and oxygen, C plus O2. C plus O2 equals CO2. And this C is graphite. Of course, we are not burning down diamond. C graphite, O2 gas, and formation of carbon dioxide gas. And this reaction is also a reaction that we will write to talk about the heat of formation of carbon dioxide, because we are forming 1 mole of carbon dioxide. And forming it from its constituent elements in their natural state. That's what we are doing. Okay. Odd. Yeah, odd. So what is given to us? Heat of formation is given to us of carbon dioxide. So this is heat of reaction of this reaction is given to us. Heat of reaction for this reaction is the same as heat of formation of carbon dioxide, the way the reaction is returned. And then we have given the entropy of graphite, oxygen, and carbon dioxide. So what we need is this equation here. We have the heat of formation, and it uses heat of formation and the entropy. So that's delta G reaction equals negative delta H reaction, delta H reaction. Oh, delta H reaction minus delta H reaction minus T delta S reaction. That's our equation. And we just put, we have delta H is already given to us. We don't have delta S. We know T is 25 degrees Celsius. We don't have delta S, so we need to calculate delta S, and that's just adding this up. So we say, all right, the equation we talked about for delta H, the products is carbon dioxide, and it's 213.7 joules per Kelvin. So 213.7 joules per Kelvin minus, that's the product, that's the entropy of the product, minus the sum of the entropy of the reactant. And that's going to be 205 plus 5 minus 205.0 joules per Kelvin minus 5.686. And that equals I have to convert this. This first thing is we're talking about here delta S reaction. It's bunching up here, sorry folks. This is delta S reaction. And that is going to be a very small number. What is that number? Anybody get it?
Three 3.0 joules per Kelvin.
Thank you. Now we take the equation for delta G. Delta G.
Don't you have to convert that into kilojoules now?
Yeah, we will do that, but we just let's get, yeah, you're right.
So then it'd be 0.0037 kilojoules.
In other words, it doesn't mean at all nothing. It means nothing. It's essentially zero. Yes. So when we talk about sig fig, you probably get washed out. But we'll see. We have to multiply it with a T. That's what we need to do. Multiply it with the temperature. Delta G reaction equals delta H reaction minus T delta S reaction. Delta H reaction is given to us. That's negative 393.5 kilojoules. And minus 298 Kelvin multiplied by 0.003 kilojoules per Kelvin. So that equals 298 multiplied by 0.003. And it's going to be a negative number, and 393 is a negative number, so adding them up, 0.5, we get 394, negative 394.4 kilojoules. What does that mean? Delta G reaction is negative 394.4 kilojoules. It's a negative number. That means this is a spontaneous reaction. That's what that means. Delta G is negative, so it's a spontaneous reaction. And That's what the number, okay, we have the right number here. Okay, good. Now, carbon graphite plus O2 CO2 is negative. This means carbon reacts with oxygen spontaneously at 25 degrees Celsius. Now, our experience says otherwise. There is a problem here. But fire is not observed at 25 degrees Celsius. We have carbon running around all over the world, but we don't.
Can I stop you for a minute?
Sure.
So if delta G RXN equals delta H RXN, but only the HF of CO2 is given, is HF and HRXN the same? No, right?
No. So,
So
this-
why did you plug and play the 393.5 to where the delta H RXN
This is-
should be?
this is right? Okay, correct.
That's what I'm saying. I'm confused because I thought that was delta HF, not delta HRXN.
That in this case, delta H formation is the same as delta H reaction. So what is heat of formation again?
Heat of formation is, the standard heat of formation is just the heat exchange to form one molecule of a compound or an ion from its content elements in their natural form at 25 degrees.
Okay, so if we write this equation, that's right there, right? Okay,
Yeah,
now this is also a heat of reaction. Whatever heat of formation, this equation also has a heat of reaction. Yes?
yes, yeah, I see it right
Same,
here in
right?
the notes. Okay, I'm
It's the
sorry.
same as heat of formation.
Yeah,
Now, this
go
is a
on.
very important point you are pointing out. I saw that number of students have difficulty understanding that. This is heat of formation, but it is also heat of reaction for this reaction. Same thing.
Because
And
it's only,
also heat of combustion.
because it's only forming one molecule.
Yes, because it's
If it
only-
was forming more molecules, it'd be different, but because
That
it's
would
just
be
forming
different,
one. Yes, okay.
and then we multiply that by that, T delta S. We have that. This
Yep.
is delta G.
That all makes sense now. Thank you.
Oh, you're welcome. So this means this reaction should happen spontaneously at like 25 degrees Celsius. But it does not happen spontaneously at 25 degrees Celsius, meaning we don't see carbon burning by itself at 25 degrees Celsius. We have a lot of carbon, charcoal is carbon. The charcoal is stored in the house until it's burned. I mean, there is nothing happening there. Well, this reaction is very, 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 very slow. So when we think about reaction being spontaneous, we also have to say, is this a fast spontaneous reaction or is it a slow spontaneous reaction? And we are not going to go into that. In chemistry 1B, you will go into, is there a fast spontaneous reaction or is it a slow spontaneous reaction? In this class, we are not going to do that. Okay, example 2. Compare enthalpy, entropy, and Gibbs free energy. Answer as directed. Enthalpy, entropy, and Gibbs free energy. Is this a state function? Is enthalpy a state function, folks? Is this a state function or a path dependent function? Let's start with Zachary. Is it a state function or path dependent function? Zach?
I'm not sure.
Oh, it's very easy. What do you see here? Is it uppercase or lowercase?
It's uppercase.
Therefore, it is a state function.
Okay, thank you.
Okay, so all three are state function. Everybody see that? So what is not a state function? Q is not a state function. And W is not a state function. T is a state function. B is a state function, and P is a state function, and delta H is a state function, of course, and delta G is a state function. S is a state function, big S. Okay, yes. Write unit of the function. What are the units of this function? Lisa?
Kilojoules over Kelvin,
Kilojoules over mole,
kilojoules over mole.
or just kilojoules is okay too. Entropy, now you're right, kilojoules over joules over Kelvin, okay? For entropy is joules over Kelvin, yes. And Gibbs free energy? Ethan, what are the units of Gibbs free energy? It's energy, what are the units of energy? Ethan?
Joules.
Joules or kilojoules, right? Can the absolute quantity of the function be known? Let's see, Alexander, can we know the absolute quantity of enthalpy? Or we can only know delta? Change in enthalpy is we can know. Can we also know absolute enthalpy of a system? Can we know absolute energy of a system? Joshua,
Yes, sir.
can you know absolute enthalpy of a system, absolute energy of a system?
No.
No. Can you know absolute entropy of a system?
I'm not sure.
Okay, can you know the entropy of this carbon dioxide as a system?
Yes.
So yes,
Okay.
we don't have delta S, we have S here. And Gibbs free energy is energy again, so you cannot know that absolute energy. So this is the difference is entropy. Yeah, yes, you can know the absolute entropy of a system. Write equation used to calculate the function. So everybody write this equation here. There are two equations for delta G reaction. So everybody write this equation and then I can talk about it, or I can just tell you which one is which. So start writing the equation. You can look at it here, that's fine. I give you, well, 4 equations, 5 minutes, fair? It's 2:27, 2:30, we will talk about it. Okay. I have it together here. So heat of reaction, mind this is a superscript 0. I cannot do anything better than that. So we'll just pretend that it's superscript 0, nothing else. And sum of all the heat of formation of products minus sum of all the heat of formation of reactant. Sum of the absolute entropy of products minus sum of the absolute entropy of reactant, not delta, absolute, and also no formation, just absolute reactant. And the third one here is very similar to this. We can just take this and put it over here for delta G. Just write down, instead of delta H, we write down delta G. And the fourth equation for delta G is delta H delta H reaction minus T delta minus minus T I T delta S reaction. These are the four equations that are the important equations. Don't worry about the other equation much at all. The ones that we did with entropy of the universe, except you need to remember that the entropy of the universe is always increasing. But that's not that can be put down in an equation because that's a law of thermodynamics. Entropy of the universe is always increasing. The scientists, they tell us that the universe is always expanding. That means the whatever the universe is made up of, energy and matter, is diluting because there is more and more volume. The volume is increasing. The amount of energy and the amount of matter in the universe is constant. Therefore, the energy and the matter, so to speak, are getting diluted. And that means the entropy is increasing. So that's another way to look at why entropy of the universe is always increasing. Okay. As I said, these are the four important equations. Understand them. You will have the equation. I would have them in front of you when I take the exam. Just write them down or print them out and put them in front of you. And then you would know which equation to use when, because it depends upon things given to you. If it is only heat of reaction is given to you, heat of formation, then you would use that equation and you'll say find the heat of reaction or heat of formation. If it also only is about this entropy, then this equation. If it is only about free energy and the free energy of formation is given to you, you would use this equation. And if delta H is calculated by you and delta S is calculated by you and the T is given to you, then you would this equation. Or if delta H is given to you, delta S is given to you, delta G is given to you, you can find temperature. So once you have these equations in front of you, then it's pretty easy to know which one to use and just do the simple calculation. Okay. All right, time to take another break. How many long minute of break you want? 15 minutes or 23 minutes?
23.
Okay, so 2:37 is 2:40 and 23 is 3 o'clock. At 3 o'clock, we'll be back. I'm gonna turn off the
Camera recording.
recording. Thank you.
The recording has stopped.
That's enough. What is the free energy of formation of octane?
Here's what I found.
What is the free energy of formation of octane?
Here's what I found.
Table of thermodynamics value of organic compounds.
I found this on the web.
Table of thermodynamics value of organic compounds.
Here's what I found.
That's correct. All right, time to get back. Okay.
This meeting is being recorded.
Okay. We finished example 1. We're going to go into example 2. No, we already finished example 2. Okay. Example 3 is what we are doing. So I have written it down here. You can copy it. We talk about it. Example 3. Calculate the Gibbs free energy, delta G reaction of the reaction. This is the reaction given to us. This is not a reaction, formation reaction. We are forming 2 moles of ammonia. That's not a formation reaction. This is a reaction, delta H reaction. The heat of formation of ammonia is negative 46 kilojoule. Heat of formation of ammonia is given, but that's not the heat of reaction of this reaction. Forming ammonia is 1 mole of ammonia. We have here 2 moles of ammonia. So we will need to multiply this by 2. So heat of formation is given. I want to find out delta G, and the standard entropy is given to me. So which equation am I going to use? This is my question. I have 4 equations, 4 important equations here. I said delta G is to be found, so it can be either this one or that one. And heat of the reaction is given, and entropy is given. So I'm going to use this equation. So I take this equation, put it down over here. Then I plug in the values. Heat of formation of ammonia is forming 1 mole of ammonia. That's negative 46. Given reaction forms 2 moles of ammonia. So we're going to multiply negative 46 by 2. So heat of this reaction is negative 92 kilojoules. Entropy and enthalpy are given. Find delta G. So I'm going to use this equation as I wrote it down here. Delta G equals delta H minus T delta S. Delta H, we just calculated it to be negative 92. So we write it down here, negative 92. T is 298 because we are given delta G is a standard. So 298 Kelvin is the T. And delta S is given to us, 199 joules per Kelvin. So there is 199 joules, negative 199 joules per Kelvin. So that's negative 199 joules per Kelvin. Now, why is delta S negative for this reaction? This reaction here. The delta is, we are told that it is negative 199 joules per Kelvin. Why is it negative? Does that make sense to us that it would be negative or it would be positive? Yes. How? The delta AS mostly depends on number of moles of gas. Because between solid, liquid, and gas and aqueous, 4 different states of matter, we have gaseous state, which has the highest entropy. So if we have a gaseous state change during the reaction, then we just look at the gaseous state change, and that will tell us. So we say, okay, I have 4 moles of gas as a reactant, and I have only 2 moles of gas as a product. So the number of moles of gas decreased because of this reaction. What does that mean? That means entropy has decreased. So it should be negative. This reaction, entropy of this reaction should be negative. So that makes sense. So that's all right. So negative 199.199 joules per Kelvin makes sense. So we wrote that down over here, negative 199 joules per Kelvin. And then we're gonna add them up. Of course, as somebody was pointing out, this is kilojoules and this is joules. So we need to convert these joules into kilojoules, or that's what we do. And so we convert that into kilojoules and we added them up. Negative 92 plus 59.3. We got negative 33 kilojoules as the delta G. Delta G, that's what we are finding. Find delta G. Delta G is negative. What does that mean? That means this reaction is spontaneous at 25 degrees Celsius. That's what it means. Any questions? Okay, go ahead and write it down. This is how you solve the problems. You have the 4 equations, 4 main equations. You just decide which equations to use. Sometimes there is only 1 equation to use. Sometimes you may have to use 3 equations. Is everybody done with this, writing this down? It's a complicated thing in a way because you have to write down negative signs and delta and superscript and subscript, and that takes a long time. I'll have to give you 2 hours for the next exam. The exam is coming up after the break. So it will be on Tuesday after the break.
What'd you say was coming up this week?
The quiz for the unit 20, 21, and 22. How do you folks feel about giving the quiz on Thursday? I know some of you work on Thursday, so that's why I'm trying to figure it out. Especially Joshua.
Yeah, I work Thursday. I actually work a 14-hour shift. We could probably do it, but I get off at 8:30 p.m., 6:30 to 8:30. If possible, I could do it Friday would be a little bit better for me, and then even Wednesday would be better.
Okay, what about Wednesday evening after the office hour?
If I'm the only one that it affects, could you possibly just make mine on Wednesday and you could leave everyone else's for Thursday?
I can try to do that. We'll see how that would work for you.
Okay. Just let me know. Thank you.
Yeah. No, you will have it on Wednesday. Whether the whole class is having on Wednesday or not, that's a different story. You don't need to be concerned about that. So after about 7 o'clock Wednesday.
Perfect.
I'll be done correcting that homework tonight. I hope to get it done tonight. So then you will have it for reviewing. And this unit 23 and 24 are not going to be in the quiz. There won't be any quiz on the last two units, 23 and 24. They will be in the exam, of course. Okay, example 4A. Excuse me. Calculate the maximum energy released to move the car. Maximum energy released to move the car. What does that mean? That means we are talking about delta G. That's the delta G is the free energy, meaning energy that is used, can be used to do work. That's what it means. When 2 moles of octane gas, this many gallons, we don't have to worry about gallons, we just use 2 moles, burns in a car engine. So we are burning 2 moles of gasoline in the car engine, and this is the equation for the reaction given to you. Assume complete burning of octane. Everybody knows when you are burning gasoline, it does not burn clean, meaning it does not just give out carbon dioxide and water, it also gives out some other stuff that we don't like, that we don't want to breathe, particulate matters, and combustion material that is only not totally combusted, not totally burned, only partially burned, and stuff like that, nitrogen dioxide and whatever. So that's why we are saying assume complete combustion. And then we are supposed to find delta G, and we are given all different delta G's of reactants and products. Delta S is not given, delta H is not given. Nobody talked about them. So which equation are we going to use out of this 4 equations? This is the question. Somebody's going to tell me which equation to use. Let's call them equation 1, 2, 3, 4. Okay, which equation are we going to use for this? Number 3, because we have all the delta G's available. Free energy of formation available, nothing else is available. So there's the equation. Delta G product minus delta G reactant, that's what is given to us. So we're gonna add them up, and that's that. So here we are. Maximum energy released to move the car, that means delta G reaction. And given delta GF, use the equation. Delta G reaction equals sum of all of the delta G product minus sum of all delta G of the reactant. So we have product is 16 mole of carbon dioxide. So 16 mole, and 1 mole of carbon dioxide has 394 kilojoules of delta GF. So we write down that 394 divided by mole. So 16 mole multiplied by 394, that equals negative 1604 kilojoules. Now we have 18 mole of water, and 1 mole of water is negative 229 kilojoules per mole. So we're going to multiply 18 multiplied by 1 mole of water, 18 multiplied by 229 kilojoules negative divided by mole, and then we have 4122 kilojoules. That's what that is. And so this is going to be a negative number. This is also going to be a negative number plus a negative number, 2 negative numbers together. Minus, this is the minus here. Delta G product is done. Now we are doing delta G reactant. we have 2 moles of octane. 1 mole of octane is a positive 6.4 kilojoules per mole, not negative, positive, minus positive 2 moles multiplied by 6.4 kilojoules per mole. And then we have 25 moles of oxygen. And we are lucky, we are in luck because the delta GF of Gibbs free energy of formation of all elements is also 0 at 25 degrees Celsius in their normal natural state. So O2 is 0. So we write down 25 mole multiplied by 0 kilojoules. So this is something, write it down. Gibbs free energy of formation, delta G of formation of elements, of all elements in the natural state is 0. So now we have these values we are adding up, and that works out to be a negative number over here, of course. What does that mean? Negative 104.10324. First of all, it's a negative number, meaning this is a spontaneous reaction. We know gasoline does not burn spontaneously, but it's, once it starts burning, it burns. And then the reaction of gasoline at 25 degrees Celsius, it does burn, but it very extremely slowly. We cannot even see it. We cannot experience the heat. So that's why it is. But it's a spontaneous reaction. That's what it means by negative delta G. And it's a very great amount of energy. You see how much energy is that? That's very big amount of energy. Ten raised to 4 kilojoule. That's a lot of energy. Okay, so write this down and then we go to the next one. All right. Next is a very simple question. Just to understand, if you burn 1 gallon of gasoline, how much energy would be produced? That can be used to do work. We are not talking about the energy that goes into heating up the surrounding, including the engine and the outside air. We're not talking about that. Only that part that can be used to make the wheels go round and round and round and round. Okay, so we're going to be talking about 1 gallon. Now here we are given this is kilojoules. This much heat is produced when we are burning 2 moles of gasoline, and that equals 0.0424 gallon. Now here we are talking about this, so that equals 0.0424 gallon. So we have a conversion factor now. This many gallons equals this many kilojoules. We are talking about 1 gallon. So we just have multiply that. 1 gal multiply with the conversion factor that we just found, and that is 1.04 multiplied by 10 to the 4 kilojoules, and negative number, of course, negative. Divide that by 0.0424 gal. That equals 2.0 multiplied by 10 to the 5 kilojoules. A lot of energy. We burn 1 gallon of gasoline. This much energy is produced that can be used to move the car. A lot of energy. Yes, thank you. Negative. And delta G is negative. That means it's spontaneous. That's what it means. Once you start burning, we know it's spontaneous. That's one way to look at it. Okay, so that was a simple dimensional analysis problem. Example 5. Calculate Gibbs free energy of this reaction. The heat of formation is given and the standard enthalpy of reaction is given. Which equation are we going to use? That's the question. Out of this 4 equations, which equation are we going to use? 1, 2, 3, or 4? Michael? Michael, are you there? Okay. We have heat of formation, that means heat of reaction, and standard entropy. And we have equation number 3, not 4, equation number 4, which has heat of formation, heat of reaction, and standard entropy, both of them in there. So that's equation number 4 is what we're going to use. Copy that, put it down over here. And plug in the values. Pretty simple. Once we decide what the equation is. Okay, 2 moles of ammonia are being formed, and we have heat of formation is 1 mole of ammonia. So we need to multiply this by 2. So negative 92 kilojoules. That's the heat of reaction. Minus T is 25 degrees Celsius, so 298 K. Multiplied by delta S reaction is standard entropy of the reaction is given to you 199 joules. So that's that, 199 joules divided by Kelvin. The only thing we need to do is to be careful that when you are doing the thing, we want to make sure that we have the same units. You see why units are so important? If we don't use the same units, we are screwed here. Okay, so 298 multiplied by 199. Oh, standard entropy is negative 199. Okay, so it's going to be plus 298 multiplied by 199. Convert that into kilojoules. I have 59.3. K and K cancel out. We have the correct unit. Kilojoules and kilojoules can be added. Of course, it's the same unit, so you can add them. So that's the other thing. When you write down the units, you can see whether you can add that or not add that. Yes. So let's see. Yeah. 92 and 59. 33. Two significant figures. Negative 33 kilojoules. That's delta G, meaning reaction is spontaneous. Reaction is spontaneous. That's what means. Okay, write that down. And then we go two more, and then we're gonna take a break. Then we're not gonna do anything more. We're not gonna get into anything more. We're just gonna talk about the exam and other things, and you have any questions on stuff like that. That's enough for today. Okay, go back over here. Excuse me. Now, this is an interesting example. It's a good example that can come into multiple choice questions or otherwise. Given the signs of delta H and delta S, determine the sign of T delta S and delta G, and comment on the spontaneity of the system with given signs of delta H and delta S. Remember, the enthalpy term for the exothermic reaction is usually much bigger than the entropy term. That means you can see that this enthalpy term here, negative 92 kilojoules. In absolute terms, it is bigger than the entropy term, 59.3 kilojoules. Most of the time, that's going to be the case, because entropy involves joules here, and then you have to convert joules to kilojoules, so the number gets bigger. I mean, sorry, smaller. Okay. In order to do this, delta S and delta S, H and delta S are given. So which equation are we going to use? We are going to use equation number 4. That's where delta S and delta S, both of them are there. So equation 4. We are going to use equation 4, but we don't have any numbers. We are going to compare. Which one is bigger? This one is bigger or this one is bigger? Most of the time, delta H reaction is bigger because it's in kilojoules, and this one would be in joules per Kelvin or something. But anyway, this would be in joules and converted into kilojoules, and that's smaller number usually, but not all the time. So delta G, the sign of delta G is going to be positive or negative, is going to depend upon the fight between these two, what do I call them? What should I call them? With these two terms. Is delta H going to win, or is T delta S going to win? Or both of them are going to win? Or none of them is going to win? Delta G has to be negative for the reaction to be spontaneous. So, yeah, I don't want that right now. Okay, so sign is given, delta H is negative. So we said delta H is negative over here. Let's get this, let's have a little bit of a space over here. Yeah. Okay, so we are talking about first one. Delta H is negative sign here. This is negative. Sign of delta S is positive. Negative sign, let's put it in the parenthesis, negative X. Negative, oops. negative x minus t, and then negative positive s, positive s. So this is going to become positive x, positive y. And both of these are negative kilojoules. Let's write down kilojoules, fine. Kilojoules. And we're gonna write down positive kilojoules over here. Now, what does that mean? If you add negative, you take this negative and you are subtracting a positive from it, that means you are subtracting this from that. So this negative, if it is bigger than the positive value over here, then delta G would be spontaneous because that's a negative sign. When would it be spontaneous? This kilojoules has to be, this absolute value of this kilojoules reaction, delta H reaction has to be bigger than the absolute value of T delta S reaction. Now, in this case, sign of negative delta D is going to be negative here. So I'm going to write down, I'm going to write down negative here, negative. Mhm. See this here, negative multiplied by positive is negative. So sign of negative T delta S is going to be positive. I'm not getting it. This negative T delta S is going to be positive. Everybody understand what we are doing here? We are saying this is going to be negative sign here. This delta H is negative kilojoules. Now this is going to be positive because T delta S is positive. So T delta S is positive. When subtracting negative from negative, we are going to have a negative sign over here. We are subtracting negative and negative, so this is going to be a negative sign. And that is the sign of delta G. This is negative kilojoules. And what is the sign of delta G here? Negative, therefore, negative sign of delta G, negative. And comment on spontaneity is spontaneous at all temperature. This is what we write down. Spontaneous at all temperature. Spont at all T. Because this is always going to be a negative number. It's not going to be a positive number. It doesn't depend upon the temperature. Temperature can be a little bit or it can be a lot, doesn't make a difference. It is always negative. Number total is going to be negative number. So this is going to be spontaneous at all temperature. Doesn't make any difference whether temperature is higher or lower. Now for another one, we will see it will make a difference whether temperature is higher or lower on the sign of delta G. We will see that too. So first one, spontaneous at all temperature. Okay. Now we go to the next one. Sign of delta H is given, positive. So now we are going to say this delta H is positive here. Positive kilojoules. Endothermic reaction. Minus sign of delta S is negative. T delta S is going to be negative kilojoule, that means. T delta S is going to be a negative kilojoules. That's what that means. So this one is positive and this one is also positive. So the total G, delta G is going to be positive. And delta G cannot be negative. Doesn't depend upon the temperature. Temperature can be higher or lower. This still is going to be negative, negative is positive, and this is already positive. So this is delta G is positive here. And therefore, if delta G is positive, it is non-spontaneous at all temperature. Temperature does not make a difference. Non-spontaneous at all temperature. Now, after the third one, I'm going to slow down a little bit and ask questions like, do you understand what's happening? After the third one. Let's get rid of this part here. All right. Now we have sign is given as negative delta H. So this is negative. Negative kilojoule. Again. Minus sign is as minus sign. And the sign of delta S given is negative. So negative in the parenthesis, we're going to have negative kilojoules. So this is negative kilojoule. The delta H portion. This is positive kilojoule. Negative T delta H is positive in this case. So now we have fun. Which one is going to win? Which one is going to give the sign negative or positive to the final kilojoules? That's the question. If the enthalpy term, this is the enthalpy term here, is bigger than the entropy term, then term provided by entropy, then it would be a negative delta G and it would be spontaneous. If it is otherwise, then it would be non-spontaneous. So these two are going to fight each other out. Now remember that this kilojoule is much bigger than this joule over here, and this converted into kilojoules. So there is that consideration. Now let's look at this. Negative kilojoules, we already have negative kilojoules, and we have positive kilojoules here. When is this positive kilojoule going to be bigger than the negative kilojoule? This is our question. Depends upon the temperature. Look at this equation here. Temperature multiplied by delta S. If delta S is multiplied by temperature, that is big, very big temperature, very high temperature, then this number is going to be bigger than that number. So what does that mean? That means non-spontaneous at higher temperature. Write the sign of delta G, positive or negative. It can be either one. It can be positive or negative, depends upon the temperature. If the temperature is very high, then this number, this kilojoule would be much bigger than this kilojoule. So it depends on the temperature. Low temperature, spontaneous. High temperature, not spontaneous. We don't need to be concerned about how high temperature because we don't have the numbers. But that's what we say, comparatively speaking. So we say here, spontaneous at low temperature or non-spontaneous at high temperature, same thing. Spont at low temp. Okay, now we're gonna stop and say, any questions? Do you understand what's going on before we do the last one? Any questions before we do the last one? All right, no questions, I guess. Now, we are given sine of delta H is given as positive. So we're gonna write down positive kilojoules. Sine of delta S is given as positive. So this is positive inside, but minus sign. So this is gonna be negative kilojoule. Positive. Yeah. Kilojoule. Sorry. Not very good at writing this way. Okay, we'll go this way. It's gonna be positive kilojoules for delta H. Delta H is going to give us positive kilojoules. Minus sign in the middle. And this is also going to be, T delta S is gonna be also giving us positive kilojoules because the sign of delta S is positive. So that's positive, and that means they're gonna fight with each other. If this number is bigger, then delta G is gonna be positive, and therefore it's gonna be non-spontaneous. If this number is smaller than this number, then this number, the delta T delta S value is going to be winning, and therefore the reaction would be spontaneous. Then that happens. So when T delta S value is going to be effective, when is it going to be effective? At what temperature? That's what we're talking about. Higher temperature or lower temperature? That's what we are talking about, because delta S multiplied by T. So this T multiplied, this T here, when would it make it so that this value would be bigger than this value? When this T is very, very high, then this value would be bigger, and then this will get negative, and this is positive. Negative minus positive would be negative, and we want to have negative delta G for spontaneity. So then that means this T is going to be at high. At high T, this would be positive. So write the sign of negative T delta S is negative here, positive multiplied by negative, negative. And this sign can be both either positive or negative. And then spontaneous at high temperature, non-spontaneous at low temperature. Tick, 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 tick. And non-spontaneous at low T. Okay, any questions? Okay, we're gonna do this and then we're gonna take a break. Example 7. Temperature, the temperature at which reactions become spontaneous, crossover temperature, is called becomes spontaneous, meaning a reaction that was not spontaneous became spontaneous. The reaction that was not going on started going on. When does that happen? At what temperature that happens? Remember, we talked about the temperature dependence upon the spontaneity of the reaction. So some reactions are spontaneous at high temperature and not spontaneous at low temperature. So when is that change happens? At which temperature the change happens? This is what we are talking about. And that temperature is called the crossover temperature, meaning crossing over from non-spontaneity to spontaneity. Crossing over from positive delta G to negative delta G. Crossover temperature. So at crossover temperature, delta G equals 0. Crossover temperature happens when the reaction becomes spontaneous. The spontaneous reaction, when it is a reversible reaction first, and then reaction would be going in one direction. But when a reaction becomes spontaneous, it is a reversible reaction. And the reversible reaction, delta G equals 0. Write it down. For a reversible reaction, delta G equals 0. For a reversible reaction, delta H equals 0 also. So we write down delta G equals delta H minus T delta S equals 0. Now,
Hold on, you just said that for a reversible reaction, delta H equals 0,
yes,
and so does delta G
Yes.
equals 0.
both of them are 0 at for a reversible reaction. So in this equation for delta G, we write down that equals 0. Positive delta G crosses to negative delta G at T, the crossover temperature. So at crossover temperature T, it is not going to be 25 degrees Celsius. It's going to be different. Delta H equals T delta H. So we are delta H equals T delta H. We are taking this equation, and since this equals 0, we just are rearranging the equation. So now we know that or T equals delta H divided by delta S. So this is the thing to remember. Once you remember that, you can easily rearrange the equation to find temperature. Example 7. The temperature, crossover temperature, that's what it's called, at which this reaction becomes spontaneous, calculated. Heat of the reaction is given and the enthalpy of the reaction is given. Heat of the reaction is given, not heat of formation. So we can just take it directly. And so we just write down the equation here. T equals delta S divided by delta S. We take this equation. We write it down over here. T equals T equals delta H divided by delta S. That equals, this is crossover temperature T. That equals 92 kilojoules minus 92 kilojoules. 92.0, may as well write that down. 92 kilojoules divided by minus 197 joules divided by Kelvin. So the answer is going to be in Kelvin as long as we have the kilojoules and joules taken care of. The units are going to be Kelvin because this divided by Kelvin over here is going to be the unit. And kilojoule can cancel out as long as we have done it right. So K equals minus 92 divided by minus 0.179. Kilojoules and kilojoules canceled out. Now we convert it into kilojoules, they canceled out. And this K is going to be on the other side. And so that's that. And there we have the answer. So let's do that. Minus minus cancels out, so positive. Of course, temperature has to be always positive. So that has to be the case. So 92 divided by 0.197 equals 464, 467 K. At 467 K Kelvin, this reaction becomes spontaneous. Before that, it is not spontaneous. After that, it is spontaneous. At 467 K, it is a reversible reaction going in both directions. At 468 K, it is going in one direction, forming ammonia.
Hey, that's only supposed to be negative 197, not negative 0.197, right?
It should be 0.197 because we converted into kilojoules. This is joules.
That's right. Okay.
That's why. Yes. Now, story time. You would say, so big deal. I mean, yes, we understand this thing that formation of ammonia, if you want to form ammonia, you have to have a very, very high temperature for the reaction to go on. 467 K, that means 273 minus 467, that's we are talking about almost 200 degrees Celsius. So high temperature. That's what this tells us. If you want to make ammonia from nitrogen and hydrogen, then you need this. You need very, very high temperature. Well, why would you want to make ammonia? Nitrogen is plenty in the air, so we have enough nitrogen. Hydrogen we can make hydrogen. So nitrogen and hydrogen can react to form ammonia. But why form ammonia? In fact, ammonia is, I believe, the third or the fourth largest amount of chemical made in the world is ammonia. Ammonia, great amount of ammonia is made every year. Why? Well, ammonia has many uses. Two main uses. Go ahead, question.
Agriculture?
Yes, to fertilizer. Ammonia is fertilizer. Ammonium nitrate is an example of a fertilizer. And we talked about ammonium nitrate. You know what happened in Beirut last year? 26 tons of ammonium nitrate went into smoke in 1 second. The whole...
Oh, that explosion.
Yes, the explosion.
Yeah, that's right. They were improperly storing it.
Yes, not improperly. They should not store, anybody should not store ammonium nitrate for that longer time. Very short time. They were storing it for 6 years. Can you remember anything more about that you can tell us?
There wasn't enough exhaust and air exchange, and it built up within the cylinders, and eventually one of the cylinders just blew, and then it blew all the rest of them.
Yeah.
Yeah.
And what was the effect of this 27 tons of ammonium nitrate blowing?
Well, they thought that they had gotten bombed. Well, at first they thought it was bombed, and then they thought it was a nuclear bomb. But it was ammonia, and that's what they thought.
Why did they thought it was a nuclear bomb?
because of the explosion and how big it was. I mean, it leveled what, like 10 miles around the explosion, right?
Something like that.
Yeah, it leveled like 10
But
miles around. So
15 miles away, the windows were broken, glass windows. And the whole port of Beirut got leveled, totally leveled, nothing left there. So ammonium nitrate.
it's amazing how things that, because I mean, people don't realize I'm from the Midwest, so we put, they put ammonium nitrate all over everything.
Uh-huh.
You don't realize that ammonium nitrate that's getting put on everything has
Yeah.
this power that, could blow up a city.
And how many people remember Timothy Leary, the person who blew up the federal building in Oklahoma? 163 people died, many of them children.
Yeah.
Our domestic terrorist. It happened in 1985? I don't remember the exact date. The guy took 1 ton of ammonium nitrate in his truck.
Yep.
And just rave the truck and let it collide with the federal building. And that was the end of the building, whole building, the tall, many story buildings. And in the basement, there was a kindergarten or children's after school program or something. That all went in smoke. So ammonium nitrate is used for also bombs. Ammonia is also used to make bombs, which would make sense to us. Ammonia has very many use. Fertilizer, very important.
Isn't it after World War II when they started experimenting with ammonium nitrate as a fertilizer because they didn't know where to put all of it?
Very good. It's World War I.
World War I.
Yes. Now, around 1912, 1911, 1910, Kaiser of Germany, the big king of Germany, wanted to even become a bigger king. You know how that is with many kings. They never think that their kingdom is big enough. They also always want to increase their kingdom. So Kaiser in 1910, 1911, around there, he said, I'm a king, but I'm a king of only a small place. I need to conquer more lands. Well, in order to conquer more lands, you need fertilizer to feed your army. The bigger the army, more the food is needed. And the army needs explosive in order to do its work. And that is needed. Ammonia is needed for that. Well, there was a problem there. Kaiser wanted ammonia. But in those days, the biggest ammonia place was Chile. And that ammonia came from the bird shit, shit of birds, guano. And this ammonia was controlled by the British. And the British also wanted to be the bigger kings. So they would not give that ammonia, the bird shit, to Kaiser. And besides that, even if Kaiser would get it somehow, the British were in charge of the oceans in those days. Their ships were everywhere, and Kaiser did not have an army, navy that was strong enough to withstand the British might. So Kaiser said to his scientist, to his chemist, we need ammonia. And Germany has been very advanced in chemistry for a long time. Even today it's advanced, but in those days, probably it was the most advanced country as far as chemistry goes. So a chemist named Haber, took up the challenge and said, oh, but we need 200 degrees Celsius temperature to start making ammonia. And that the cost is prohibitive. The cost is prohibitive. We need to change this somehow. To bring this cost down, we need to bring down the temperature at which the ammonia is formed. And people say, look at the equations. Look at the delta G equations. At that time, delta G was well known. You have to have 200 degrees Celsius. So, oh, well, is there a way to go around this delta G temperature? And we are not going to talk about how to, the mechanism of going around it, but they figured it out. They said, okay, what about using a catalyst? A catalyst is a chemical that makes the reaction go faster without itself getting affected. So, like we have catalytic converter in the car that converts nitrogen oxide into less harmless exhaust. And these catalytic converters have a lot of metals that are very precious metals, often like platinum and stuff like that. And so these days, the catalytic converter of this car, what is it called, Prius, are being stolen because the converter has this precious metal, and that's the price is very high, so they are being stolen. Anyway, going back to our story, Haber, the German chemist, figured out how to produce enough ammonia at lower pressure and lower temperature. The pressure also involved because it's a gas, so the pressure is involved. Temperature is not the only thing. So the pressure is involved, and he figured out a way to do it in 1911 or so, and 1910 or so. And then they started making ammonia. And in 2 years, they had enough ammonia to make fertilizer and their ammunition. And then Kaiser went to war. Kaiser went to war. So this Gibbs free energy is a very important thing. It's, I mean, you know, it is connected with World War I. Okay, let's take a small break, and then we just take your questions, and I'll talk about the exam. That's what we are gonna do. Let's see, a 15-minute break, 14 minutes break, come back at 4:20. I'm gonna turn off the recording.
The recording has stopped.
Okay, 4:20. And think about the questions you have. All right. Questions time, your time. If you don't have any questions, I'll talk. But nothing, not a new topic, no. I had said that I would do the last problem on the homework. The heat of reaction, not the Hess's law of heat summation. So I can do that one. Diego, you have anything to say? Mr. Gonzalez Soto? Mr. Gonzalez Soto has nothing to say? Okay. Question time. You have any questions or you want to think about questions? All right. Okay, Lisa,
Hi.
you have any questions?
I don't. I'm actually working on the unit 23 and 24 homework. I know you haven't posted it, but I'm just doing the sheet. So if I have questions, I'll let you know.
You need 23 and 24 homework.
Yeah, the assignment that you put in the guidebook.
Oh, I see. Okay, you're doing it in the guidebook. Okay, because I
Yep.
have not put that together yet. Okay,
No.
guide is okay. I'm not-
For the quiz, it's gonna be 20, 21, and 22, right?
Yes, not 23 and 24. That's correct.
Okay.
Makaya,
We go over questions 3 and 5.
question 3 and 5 in the homework?
Yes.
Okay, let's do that right now.
Professor, what day is the exam going to be?
It's gonna be on Tuesday,
Okay, sweet.
Of spring break?
after spring break, yes.
Awesome. Okay.
So Makaya, 3 and 5, 3 here, write the equation. Yeah,
No, on the very top, not in the question 24.
oh. There were a couple of mistakes. So that's what you were talking about. The system perform work by, you cannot answer this question. There is nothing work by what. I forgot to write work by something. I changed it, but I don't think it's there anymore. And it's not here. And phi is the same thing, chemical system represented by the equation, or this can be done. A chemical system is represented by the equation HCl, aqueous, plus NaHCO3 solid. Okay, H2O plus CO2 plus NaCl. This is a gas forming double replacement reaction. And what is the sign of pressure volume work done by the system? Well, there is the carbon dioxide gas being produced. There is no gas in the reactant side. There is 1 mole of gas on the product side. Gas is being produced, and therefore the gas is going to expand the volume of the reaction. And in order to expand the volume of the reaction, it will have to push at the surrounding, meaning it will do work on the surrounding. So it would be negative sign, but what is a sign? You cannot answer that question. It's not true or false question. My problem. Those two are my problem. So I'll take care of them.
Yeah.
Now let's go to the last problem here. Use gases law of Fitt summation and give equations and given equations to calculate delta H reaction of the hydrolyzation of glucose. Hydrolyzation, as I explained, meaning breaking down using water. There are many reactions in the body. Human body happens where water is used with enzymes in order to break down certain chemicals like sucrose. So when we eat sucrose, the body would use a particular enzyme, sucrase, that's called, in order to break down into 2 sugar with 6 carbons in it. Sucrose, you might remember, is called C12H22O11, right there, C12H22O11, that's our sucrose. And then it can be broken down into 2 sugars with 6 carbons, like glucose and fructose. Those are the 2 sucrose that are the two sugar that are broken down products of sucrose when you add water to it. Now these are called carbohydrates, and the reason they are called carbohydrates is that it's like a hydrate. It's not a real hydrate. Like, we understand real hydrate, CuSO4 5H2O, that's a real hydrate. But carbohydrate is not a hydrate in that sense. It just means that it has the oxygen-hydrogen ratio. The hydrogen-oxygen ratio in carbohydrate, in sugar, is 2:1. That's what it means. And that is true. All sugars have 2:1 carbon-hydrogen, oxygen-hydrogen ratio. Look at this, 2 hydrogen to 1 oxygen, 2 hydrogen to 1 oxygen. This is 2 hydrogen to 1 oxygen. That's what carbohydrate, the name, comes from. So sugar, as we eat it, broken down into, the first thing is broken down into glucose and sucrose. Or was it galactose and sucrose, fructose? I forget. There could be another. There is another sugar called galactose, and I don't remember right now which is broken down into. Okay, anyway, that's not important for us. We just read all those sugar, the glucose, fructose, and galactose, they have the same formula, C6H12O6. What makes them different is something we are not going to talk about. Okay, so burning sugar is a highly exothermic reaction. We can find this out by using a bomb calorimeter. So that's what would happen. This is the combustion. We have lots of energy. You have seen burning sucrose. We saw that demonstration. Now, hexose sugar is converted to alcohol by fermentation. So hexose sugar is meaning hexa means six, means 6 carbon, sugar with 6 carbon. OSE means sugar. All the sugars have the last suffix OSE. Glucose, fructose, galactose, maltose, dextrose, they are all sugars. They have OSE at the very end. And they also say, sometimes they say how many carbon in it. So hexose are all sugars with 6 carbons in it. Like glucose and fructose and galactose, they are hexose, they have 6 carbon in it. They are different sugars, but they have 6 carbon and 12 hydrogen and 6 oxygen. All of them have, as I said, same empirical formula and same molecular formula. How are they different? That is interesting, but we won't go into that. Okay. So by fermentation, so this everybody realize fermentation reaction is, that's what alcohol is made by fermentation. So that's the alcohol making reaction. And decomposition of hexose sugar, we have this much energy, heat of decomposition, breaking down of dextrose sugar. Alcohol is burned to form carbon dioxide and water, and that happens all the time. These days, some gasoline has 10% alcohol in it. So that's what's happening here, and that's a fair amount of energy there. And these things are given, and these 3 reactions are given, and then you are supposed to find to calculate delta H reaction of hydrolyzation. This reaction is called hydrolyzation. This happens in the body at 37 degrees Celsius, which is very close to 25 degrees Celsius. So what is the delta H? We want to find the delta H reaction for this. So we are going to manipulate these 3 equations in such a way that when we add up those 3 equations, we get this final equation. And how do we do it? I have written down the steps for you. I'm going to go over the steps again. Step number 1, we look at the final equation that we are supposed to have. And we say, all right, what is the reactant in the final equation? Reactant is sucrose. Let's found an equation here that has sucrose as a reactant. Okay, well, the first reaction has sucrose as a reactant, so we're gonna take that equation and write it down. And then we're gonna say, okay, this equation has a sucrose as a reactant, and it also has 1 mole of sucrose as a reactant, which also this equation also has 1 mole of sucrose as a reactant. Therefore, we're gonna leave this equation alone. We're just gonna write it down like that. We want 1 mole of sucrose reacting. Okay. Now sucrose is taken care of. Now we go to H2O. So H2O is a reactant over here. H2O is a product over here. Now that's an interesting thing now. H2O is a reactant and H2O is a product over here. Well, we need to have lots of H2O as a reactant on this side in order to have 1 H2O as a product. And in fact, we need to have 12 H2O on the reactant side to get rid of this 11 H2O. So let's look at the H2O, which equation has H2O in it. This equation number 2 has no H2O in it. This equation number 3 has H2O in it, but in the wrong place. It's in the product side. We want it in the reactant side. Well, we flip the equation, it will be on the reactant side. So we are going to flip this equation. We are going to write a 3H2 and 2CO2 as a reactant and the other thing as the product. So we take this. And we say, because we flip the equation, we're gonna flip the sign. Positive 1.364 10 raised to 3. Positive 1.368 multiplied by 10 to the 3. Oops. 10 to the 3 kilojoules. Now, we also say, hey, I need to flip this equation. So I'm gonna go 3H2 over here, 2 over there, dang, 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 dang. Plus 2H2O, giving us yeah. Okay. Now, but we need 3H2O, we need 12H2O in order to have 1 H2O left over here. Also, so we need to multiply this by 4 in order to get 12H2O. So we're going to multiply this by 4. The whole thing to be multiplied by 4. The whole thing, all of it. Now we're going to write down what is available now. We multiply by 4, 12H2O. I'm not going to write liquid, we understand that. Plus 8 CO2. Not going to write gas. We're going to just say that, okay, it is a gas. Okay. Multiply by 4. Alcohol. Plus 3 multiplied by 4 is 12O2. And we're going to multiply this by 4. So that's going to be 1368 multiplied by 4 gives me 5.472. 5.472 multiplied by 10 raised to 3 kilojoules. Okay, so I need to get rid of this. I took care of that. Okay, now the next thing I need over here, comparing this, I need 2 moles of C6H12O6 as a product here. Well, which equation has C6H12O6? Here, I have this equation as C6H12O6, but it is a reactant. I need a product. And I also have only 1 mole here. I need 2 moles. So I'm going to flip this equation and multiply by 2. Flip the equation and multiply by 2. That's what I'm doing now. I'm going to copy the equation, flip it, and then multiply by 2. So it's going to be multiply by 2, 2 in the parentheses, everything else. I have negative 68 kilojoules for this delta H. So here, because I flipped it, I'm going to convert this into positive 68. And I'm going to multiply the 68 by 2 in order to get 136. So I'm going to say 100, positive 136, write down this positive because that's important. And this, I forgot to write down, what was it? The negative here. And 2 multiplied by 2 is 4. And 2 multiplied by 2 is 4. And this is going to be 2. Now, I have used up all these 3 equations. I have taken care of this. So all this, adding up these 3 equations should get me this equation. Very likely, unless I made a mistake in some little calculating or something. So we add up plus, plus, and plus. Okay, so see 12H12O6, one of those. 12 of oxygen is a reactant. So we are putting all reactants together, plus 12 of H2O plus 12 H2O plus 8 CO2 plus 4 CO2 plus 4 alcohol, C2H5OH, that's the reactant. That's the reactant. So what's going on here? I see. What's the problem here? Leave it alone. Okay. And the products, on the product side, we have this. Two of that. We have here two of these plus, and we have this product side here. All right. So now we say, what is common on both sides? We have C12H22O6. That's fine. That's just like that. 12O2. And I have 12O2 on this product side. Right there. This one that I forgot to put in there. I forgot to put in also 4 C2H. Yeah, I also forgot to put this in. Okay, the product. So okay, so I say I have 12O2 here, and I have 12O2 here, so that cancels out. I have 8 CO2 plus 4 CO2 is 12 CO2. I have 12 CO2 here as a product, cancels out. I have 12 H2O as a reactant and 11 H2O as a product. So 1 H2O left over as a reactant. So that's the 1 H2O left over. I have 1 C2A, 1 sugar as a reactant. I have 1 sugar as a reactant. I'm fine. Now, what is left over here? 2C6H12O6. I have 4 alcohol, C2H5OH. I have 4 alcohol over here. And this is, I wrote extra. This here is something that should not be there. It was written extra here. Yeah. I already wrote 2C6H12O6 over here. Hmm. That's as a product. And right there as a product. So 2,6,H12O6 I should have, I wrote down twice. So then 12H2O becomes 1H2O here. And this is 2 here, that's it. So now I have the original equation here, this original equation here. Let's see, how can I show it to you there. There, plus 1H2O. Everything else canceled out, equals 2 of this. So that's 1H2O equals 2 of that, 2 of the hexose sugar. So I have the original equation back here. So now what I need to do is to add these up. Minus, minus, plus. Oh, this one we flipped here, this one here. This one we flipped. Yeah, we flipped that one. So we need to change the sign of it. So this here's 4H2O and 2. Yeah, the sign here needs to be changed. Positive. So you have to be very careful with the signs. That's what it is. In the exam, if you make a mistake like this, I would take off half a point or something like that. I'm not gonna, mathematics, as long as you show me that you understand it, most of the points you get. So here we are adding up 5640, that's negative. 5472, 5472 plus 136 minus 5640. Yeah. 5. $32. And minus 32 kilojoules. That would be the answer. Minus 32 kilojoules is given the answer. Okay. So that's how we deal with this this Hess's law of heat summation. Now later we'll be also doing a Hess's law of heat summation where we'll be using 5 reactions, not 3 but 5. But they would be simpler reaction. They would not be very complicated reaction. And I won't ask you such a question with 5 equation for Hess's reaction because it will require half of your time, which is going to be 2 hours for this exam. So this is what we do for Hess's law. All right, any questions?
I have a question.
Yes.
For canceling out the equation, can you just do it inside before you add it all? Instead of rewriting everything and then canceling it?
Yes, you can do that. That would be, I could have done that, but it's easier to do it with your writing with your hands. If you are doing that, that's a little easier.
Okay.
Ah, Hess's law of its summation, once you understand it, as somebody was pointing it out, it's pretty easy, nothing much to it. And don't worry about a little mistake that you make in, not writing down the sign or something. Hopefully you won't make that mistake, of course. In multiplication easy, you just multiply 2, 3, or 4, or you flip the equation. So what does that mean? This equation here is negative 32 kilojoules. That's what. So actually energy is made available to the body by doing that. So you eat sucrose, and 1 mole of sucrose breaking down into 2 hexoses, 2 different sugars, body gets negative 30, body gets 32 kilojoules of it. Sugar has lots of energy in it. And we have done some calculations with that. So anyway, 1 teaspoon of sugar, 9 grams or so. We calculated it. In order to burn that, you will require to do about 180 push-ups. Yeah. I did how many push-ups today? 22. So I didn't burn up much sugar at all in that way. Of course, as many of you probably know, weight management is a complex issue. It's not just something simple as how much you eat and how much you exercise. It's not like how much you eat and then how much energy you're using, how much work you are doing, how much energy you are using up. Subtract one from the other. It does not work like that. There is a base metabolism. Everybody has their base metabolism. And that depends upon how much energy you are using in order to just sleep. While you are sleeping, of course, the body uses energy. And if you have high base metabolism, you're going to be skinny or you're going to not have much weight. If you have low metabolism, well, chances are that you are going to have a little fat on your body.